So welcome everyone. Welcome back to Power System classes. And like I took a small break because I was not really well for last 1 week, so that's why uh, I was I was in hospital, so I couldn't take the classes for last 1 week. So we'll be continuing our discussions on, and we will be continuing our discussions on um, electrical power system analysis. So the first part of the electrical power system analysis was transients in electrical power system. So that we have covered. We have covered the transmission line model. We have covered the Beverly lattice diagram and all those things. So now we will be focusing on something known as network calculations. Okay. We will be looking more closely into network calculations. Okay, so we'll be looking at network calculation. So what is the thing what we are going to study in this particular session is Y bus and Z bus. Okay, so these are the two important parts. First one will be Y bus, and second one will be the Z bus calculation. Okay, so Y bus and Z bus, these are the two important thing what we have to study in this particular thing. So we can look at. So one of the most important thing what you have to know here is Y bus is basically the inverse of Z bus. Okay, so Y bus is basically inverse of the Z bus. So the one thing that will come to your mind is like if you know how to find Y bus, then we can actually find the Z bus, because if you take the inverse of the thing. But the main problem with the inverse, if you check what is basically the inverse, so the inverse is not so easy to find out, okay, because the inverse operation is order of n cube operations we have to consider. So inverse is not easily we can take. Like if you think about very small, like 2 by 2 or 3 by 3, then we can easily take the inverse. But if you consider like 1000 bus or 2000 bus system, then the matrix will be almost like no, like 10,000 cross 10,000, right? So what happen is you cannot directly find the inverse. It will be very it will be very heavily computationally intense process. So that is not very easy to find. So that means there are methods to find Y bus and there are methods to find Z bus. Okay, these are like independent. So don't think like this. Once we find one, the other can be easily found. That is not practically not really possible. But like there are some conversion things are available, and you can do that. Okay, that's a different issue. But uh, the thing is that don't actually like think in your mind that if you find Y bus, take the inverse, and you find Z bus. That is not practically possible. Okay, so this is the first one we have to think about it. And the majority of the interviews they might ask, why can't you directly take the inverse of the Y bus so that you can directly find the Z bus? Okay, so the answer you have to give is inverse is computationally very intense. So taking inverse of a very large matrix is not practically not possible. Okay, so So there are methods by which we can find Y bus and methods by which we can find Z bus. Okay, so we have to study separately. Okay. So this total module what I have going to teach today can be divided into three parts. First one is the equivalent source. Okay. Second one is Y bus formation, and third one is Z bus formation. Okay, so these things you have to, this will be actually, I'll be looking at these three things today. Okay, what is basically an equivalent source, Y bus and Z bus. So the equivalent source is very important because in most of the power system we will be writing the Y bus. Okay, so I'll be saying where we require Y bus and where we require Z bus. Y bus we normally use in power flow studies. Okay, for power flow studies we use Y bus, and for Z bus we normally use in fault analysis. So these are the important things you should remember. Y bus we normally use for power flow studies, and Z bus we normally use for fault analysis. Okay. So I hope you will, because we will be looking at these two things in the coming classes. So I will be just explaining in this class how to find the Y bus and how to find the Z bus. Okay. So first one is the equivalent source problem. Equivalent source. So assume that we have a system of this form. Okay. So let this be EG, some generated voltage, and this will be source resistance ZS, and some load resistance ZL. Okay, so there is the current. Let this current be some. Okay, you can just let this voltage be VL. Okay, that is the voltage across the load. So what is VL? VL is the voltage across the load. Okay, and ZL is the load impedance. Okay, so these things you should take care of. Okay. So now what we can find what is basically this current. So we can write VL is basically EG minus IL into ZS. Right. So I hope you understand what is VL. This voltage plus minus this voltage will be EG. This voltage minus this current. Let the current be IL. That is the current flowing through the load. Okay. So EG minus IL into ZS. Okay. Now we are considering a separate situation. So I will draw in a green one. So that situation is something like this. There is some current IS. Here the voltage, let this be some ZS, and this is basically ZL. Right. So let this current IS is coming here, and this load current remains same. Okay, this is IL. Okay. So now we can find what is VL here. Okay. So that means VL in this case. Okay. So VL will be equal to IS minus IL. That is the current flowing through this resistance. IS is coming here and IL is going here. So IS minus IL into ZS. Right. That means VL equal to IS into ZS minus IL into ZS. Right. So we are saying that these two circuits are equivalent. Okay. We assume that these two circuits are equivalent. Okay. So this circuit and this circuit is a basic circuit. So that means these terminal conditions are also same. So if we equate the terminal conditions, what we can find is this VL is same as this one, right? That is the LHS is now same. So the RC should also be same. That means EG will be equal to IS into ZS. Right. And IL ZS is same here and same here. Right. So that means now what is happening here? We have a voltage source series with a resistance that we have converted to a current source parallel with a resistance. Right. So what we have to do is we have to, in order to convert an voltage source series with a resistance, what you have to make is you have to cut at this particular point, then find a new current. That value of that current will be the value of the IS will be, what will be IS? IS will be EG by ZS. Right. So we will cut at this particular point, then replace that voltage with a current having a value. So what is the value of the current? EG by ZS. Right. And parallel with the resistance, and value of the resistance will be same as the resistance. So, and similarly, if you want to convert this to this, what you have to do is you have to just multiply with, we have to write a resistance in series with a voltage source. So just multiply IS and ZS. So that will be IS into ZS, that is basically EG, right? And it will be ZS, right? So this is how we will be actually doing the source transformation. So because source transformation is very important for basically known as something known as a nodal analysis. Okay. So for nodal analysis, we basically use a source transformation. Right. Okay. So I hope you understand this one. Okay. So now we can think about another problem. I hope you just write this because I'm going very slow today because I'm just recovering from the disease. So we can just write down these things and we can go forward. Okay. Okay, now just consider some circuit like this. So this you might have studied in your network analysis class. Okay, so this is something known as like this is a current actually source flowing through this one. So this can be like represented similar to this way. Both are now same. Okay. So these two are electrically equivalent because if you check this node, this is the extra node we have added, right? So what is happening is some current is actually coming and some same amount of current is actually going from here, right? That means this nodal equation will be automatically satisfied. So this type of equations are very important, like when we write the nodal equations, like we can directly write a node equation in this one. Similarly, if this is something like an voltage also, we can actually write in this particular form. So these things what you study from your network analysis class, we have to use a very small bit of that thing in here. Okay. So this is very important. They might ask you in interviews whether these two are equivalent. Okay, these two are equivalent because the current is actually coming here and the same current is going here. So the nodal equation will be automatically satisfied here. Okay. So everything will be actually same only here. Now we can look at the node equations of a power system. Okay. Now we can draw a single line diagram. Assume there is a generator here. Okay, I will draw another page. So much easy for you. Okay, so this is the first bus, second bus, and third bus. Okay, and sorry, first bus, second bus, third bus, and this is the fourth bus. Okay, and we can consider one of the buses the reference bus or the like something else a slack bus. Okay, like we can consider this as reference or any one as reference. So assume that we are actually grounded because here everywhere there is a source there, right? So we can just ground this. So this will be something like a reference bus 0. Okay. Like, or we can give some E angle 0 or something that will be the reference bus. Okay. Like it depends on the problem. So let this be EA, EB, EC. Okay. So there are 3 generators. Okay, here. And there are some transformers also here. The first step is to draw the single line diagram. Okay, so single line diagram means we have to convert this everything to its corresponding electrical equivalent. Okay, so okay, so in some textbooks, what they will use is they will use a separate ground. Okay, like not this, they are not actually putting this as the ground. We have some ground which is the ground of all these, all these thing is grounded to 0. All these sources are grounded to 0. Okay. There is some node here, so where all the generators are basically grounded. Okay. So there are different ways by which we are saying everything is same. Now we can convert this one. Okay. So this is the voltage source. Then there will be 2 impedance. So one impedance is coming from the generator, and there is the impedance of the transformer. First impedance is from generator, then impedance from the transformer. So similarly here also there is some impedance from the generator, some impedance from the transformer. Okay, so up to this part is now done. So we can draw the first base, second base, and third base. Okay, now between base 1 and base 4, there is a transmission line. So assume that base 4 is here. So we can consider a transmission line here. So between now there is no connection between this and this. Okay. Here there is a transmission. Okay. Now there are 2 bases actually coming from. One is coming here, 2 transmission lines. Okay. Okay. So now the network is done. So let's assume that this is basically the first bus. This is V1, V2, and this is V3. This is basically V. Okay. Now we can. So this will be EA, EB, EC. Now the total impedance. Let this total impedance be something like ZA, ZB. Let this be ZC. Okay. then we can write some A, B, C, Z, D, Z, E, Z, F, and Z, G. Okay, so like this. Now the first step is we are actually considering the nodal network. Okay. So what is the advantage of a nodal network is that if one of the node is considered as a reference, we have to write only n-1 equations. Okay, that is the basic advantage of a nodal analysis. Okay, so we can write the equations for each and every bus. Okay, if you write the equation for first bus, sorry, the first step is to convert all voltage source to current source. Okay, we have to use a source transformation to current source. So we can do that by using the source transformation. So I will just draw the equivalent thing here. Okay, so what will be the thing? So there will be a current source actually coming here, and this impedance will be in parallel to this. We'll just draw one minute. Okay, so this is actually connected to bus 1. So there will be bus 2 and bus 3. So similarly, there is another. So why you can directly assume, like, you can think like why I should convert everything like this. Okay, because these things what we are doing in our mind in such a way that we are actually implementing everything in a computer. Okay, so this will be very easy for the computer because this 2 or 3 bits we can actually directly use by hand. Okay, we don't have to worry about all these things, but while we implement these things in a computer, so this will make it very easy. So if you go to your your MTech thing, there will be a separate course, computer control of power system or advanced computer control of power system. So there we will be studying why we are actually considering all these things, because there we will be actually looking at something like more than having 100 or 200 or 300 buses. Then writing by hand will be difficult. So if you write an algorithm in a computer for each and every bus, the computer will do everything. Okay, so that's why we are actually looking at all this, and we can have a ground here. This will be 0th node, 1 node, 2 node, 3 node, 4. Okay. So now, we are actually taking 0th node as the reference. Okay. So we don't write equation for 0, but all other equations we have to write. So now we can write. So this is current be I1, ZA, I2, ZI3, ZB, ZC. Then this will be ZD, ZE, ZF, and ZG. Okay. So we'll be writing this one. So the current I1 will be equal to this voltage V1 into this is Z, right? So I equal to Y into A. So that will be YA. V1 into YA plus V1 minus V2 into YD plus V1 minus V4 into Y. Yeah, right. We can write like this, right? So the current incoming current I1 will be all the sum of the currents that is outgoing. So this way we can write this. So similarly for I2 also we can write. I2 will be what we can write. I2 will be this current will be basically V2 minus V1 into YD plus V2 into YB plus V2 minus V3 into YC, right? All the nodal currents we are writing. Similarly, we can write I3 will be equal to, this is I3 will be equal to, there is no connection between 1, so that will be 0. So 1 and 3, so there is no connection there. Then we can write V3 minus V2 into YC plus V3 into, sorry, E, right? So YE, Y. So V3 into YC plus V3 minus V4 into YG, right? So that will be I. Now, if you check this one, there is no current source, right? So we can write something like, I'll just we can write 0 equal to V4 minus V1 into YF plus V4 minus V3 into YG, right? So what we'll get a set of currents, right? So we can make this in a matrix form. So that matrix form is so if you check this, so we'll get something known as a matrix. So I'll just I'll just write here this I1, 2, I3, I4. So I4 is basically 0. Okay, so we can just write this I4 equal to, we can write I1 YA, then minus YD, then 0, then minus YF, right? Then the second one will be minus YD, then YB minus YE 0. The third one will be, and right here, there is here, then minus YE, then YC, then YG, right? And fourth one will be, if you check here, minus YF 0, minus YG and 0. Right? This into, so V1, okay, V4 is there, sorry, YG into V4, sorry, YG plus YF is there. Okay, so you have to sum everything. So sum will be actually 0. Here also you have to right. So V1 into YA plus, so YA plus minus YD. So here also you have to write YA plus YD, right, plus YA. So you have to write like this. Okay. So other things are also there. So you have to contain and care of it. So into here also you have to write this plus this will be coming. So YB plus YD plus YE. So here YC plus YE plus YG. So these things will be also coming. And so this will be into V1, V2, V3, V4. Right. So this is very important. Okay. So this type of a base, this type of matrix is basically known as the Y matrix. Okay. So if you define what is a Y matrix, I will just write like this. So I1, I2, I3, I4 will be equal to y11, y12, y13, y14, y21, y22, y23, y24, y31, y32, y33, y34, y41, y42, y43, and y4 into v1, v2, v3, and v4. Okay. So what is y11? So y11 will be, we can write like I1 equal to y11 v1 plus like y12 v2 plus y13 v3. So assume that all other buses v2, v3, v4, v2, v3, v4 equal to 0. Okay. So that means if v2, v3, v4 equal to 0, or all other buses are actually grounded, then we can define y11 as the current I1 by V1. Okay. So if all other buses are grounded, then the ratio of the current flowing through the same bus and the voltage at that particular bus is given by actually Y11. Okay. So Y11 will be equal to V1 by, sorry, I1 by V1, I1 by V1, given all other buses, V2 equal to V3 equal to etc. up to Vn equal to 0. Okay, this is basically. So similarly, we can check what is y12. So y12 will be I1 by V2, and all other buses are basically 0. Okay, so in this way we can actually find it. So if you consider a very large network having like more than 10,000 or 20,000 buses, then the Y matrix will be almost like this, and it will be basically sparse. Because in Y matrix there will be actually connections between nearby buses only, like so there will be the no connection between first and 7,000 bus, right? So 7,000 bus will mostly have connection between 7,000 minus 1 and 7,000 plus 1, or 7,000 minus 2 or 7,000. So like 3 or 4 buses connections will be there. So that's why we don't need to store the whole matrix. That means we don't want to store all the zeros. Sparse matrix means most number of elements in that particular matrix will be 0, right? So we don't want to store all the elements. So we will just keep an array of which, first position, which position we have numbers, and we will save that number only. And whenever we need the Y matrix, we will create the Y matrix from these two small arrays. Okay. That is why we normally do it in the computer coding. Okay. So that is one of the important advantage of Y-bus. Y-bus is always a sparse matrix. But if you take the inverse of a sparse matrix, it may not be sparse. It most probably will be a full matrix, unless it is very close to identity. Okay. So unless it is very close to identity, it will be a full matrix. That means storing Z bus requires a lot of space, because we need to store all the elements in the Z bus. But storing Y matrix is very easy, because Y matrix is a sparse matrix. Okay. So I hope you understand how we are actually looking at the Y matrix, and you can write this and this one. Okay. Then we can look at the next aspect of IMS. So generally we can write Ik equal to sigma n equal to 1 to n y kn pn. So this equation is very important, because this we will be using for our load flow analysis. This is the same equation we will be going to use for load flow analysis. Okay. So just be careful with the equation. Ik equals sigma n equal to 1 to n y kn pn. Okay. So just look at this, and we can move to the next part. Okay, so now we can look at another aspect of nodal analysis, that is basically known as node elimination. Node elimination. Okay, so what is basically node elimination means? So the last thing what I have the best what we have drawn is something like this, I1, I2, I3, I4 was 0, right? That will be equal to Y11, Y12, Y13, Y14, Y21, Y22, Y23, Y24, Y31, Y32, Y33, Y34 times P1, P2, P3, P4. Right. So now we can check here. And thing is that this Y matrix is always a symmetric matrix. Always a symmetric matrix. So now we will do a small manipulation. Something like this. We'll draw two lines, okay, here. Like this. Okay. Okay, so there is one more. Sorry. So Y41, right and right. Y41, Y42, Y43, and Y44. Okay. Now, because there are 4 equations here, so there will be 4 by 4. Now we will make a column like this. Okay. Now this can be written as, here also will draw like this, and here also will be drawn. Now this can be written as some matrix A or some matrix I, right? Then some matrix 0. Okay. So this is this I1, I2, I3. This matrix is basically our I matrix. Okay. This can be written as some A matrix. So this total, this will be Y matrix. Okay. Y matrix. Then we take this as L matrix. So this will be L transpose, and this will be something known as an M matrix, right? Because we can check Y is basically 3 by 3, right? So L is basically 1 cross 3. This is 3 cross 1. The M is 1 cross 1 into basically V. Then V4, right? This is also 3 cross 1. This is 1 cross 1. This is V1, V2, V3. Okay, that is basically 3 cross 1. And this is 1 cross 1. Right. Now, if you write the equations in the matrix form, what we get is the matrix I will be equal to Y matrix into V plus this will be equal to, first row will be equal to then L transpose into V4. Right. Now we can write 0 equal to L times V plus M times V4. Right. Now we can get a small manipulation here. So we will find here minus LV equal to M times V4. Right. So that means what is V4? So V4 will be equal to minus LV by M. Right. Now we will substitute it here. So we can write the matrix I will be equal to Y times V plus L minus, sorry, because there will minus will be coming from here. So minus L transpose L V by M. Right. So that means matrix I will be equal to Y minus L transpose L by M divided by into V. Okay. So now check here. So this is 3 by 3, right? So Y is also 3 by 3. L transpose will be also 3 by 3. Now V is also sorry, 3 cross 1. C will be also 3 cross 1. So now using if there is no current source actually coming there, we can eliminate that particular node, right? So that means it's a 4 by 4 matrix. We have to solve only a 3 by 3 matrix now to find the value of different V. So once we got the value of V, we can substitute it here to get the value of V4. So substitute the value of V here to get the value of V4. So that means if we have a 10,000 or 12,000 bus system, so in this only 6,000 matrix is having some kind of a current source, right? So that means we can actually for finding, because in a linear algebra perspective, A by B or A inverse into B will be the most computationally expensive. So if you solve, instead of solving 12,000 cos 12,000, we can easily solve a 6,000 cos 6,000, and with the each solution we can go back and back substitute and find this particular value of voltage. That means the computation is now seriously reduced, right, by this particular node. So this particular elimination is known as Cron's reduction. Known as Cron's reduction. This is known as Cron's reduction technique. Okay. We should remember this. This is particularly known as the Cron's reduction technique. So by this, actually, we will be using a lot of things in the normal computer programming. We'll be converting. We'll be finding those voltages of the buses which is having an voltage source only. The other one we will be actually doing some back substitution, and we will be actually finding this. That will be computationally much easier than finding the entire A inverse into B. So even if you take A inverse into B here, you will get a same same equation. There will be any problem with that. Okay. I hope you understand the thing. Now we can do a small example. Okay. So we have a 4-bus system. So similar, if we substitute the values of all the buses what we have given here. Okay, something like this. 9.8. There is no J. Okay, J is given. Okay, so we have to reduce this particular. This is basically V1, V2, V3, and V4. This is I1, 2, I3, and I4. Okay, so this will be 0. Okay. So now we have to draw like this. Okay. Now we have to find the current. We can write I1, I2, I3 will be equal to this matrix. So we can align this small matrix as some y minus what was the equation? Y try y minus L transpose M by M, right? So this was our L matrix and this is L transpose. So we can just check this will be 3. So L transpose will be into L. So that is basically L transpose is 3 cross 1, L is 1 cross 3. That will be 3 by 3, correct. Divided by J 118.0, right, into V1, V2, V3. Right. So from there we can find the matrix or something like this. The new matrix will be some. You can just do it and check minus 8.411, J 1.38, J 6.2, J. This will be symmetric. Okay. J 1.38, J 6.2, minus J 6.9, J 4.7, then minus J 10.9 and J 4. Okay, so this will be the thing. Okay, so this we can solve instead of solving this 4 by 4 matrix, we can actually solve a 3 by 3 matrix. Okay, this is basically known as the Cron's reduction technique. So by this, we will be actually closing our discussions on the Y bus and the Z bus. We will be discussing on next class, and with the Z bus, then we will start the load flow analysis. Okay, thank you, and we can meet in the next class.